Today we are going to learn the first chapter of class 12 mathematics, that is relations and functions. In class 11 you have already learned about relations and functions. So just here we need to add some more of our knowledge in this chapter, that's it. So what is a relation? Relation is just a subset of A cross A. That's what we have learned in class 11. So now we are going to learn different types of relations. The first type of relation is the empty relation. What does the name suggest? The name suggests that there is no element that is present in this empty relation. So what does the definition say? If no element of A is present in the relation, that means that the relation is equal to the null set. The relation is equal to the null set. You represent the null set like this, or you represent it in this format where there is no, there is no element over there. And this relation is based on A cross A. So the second type of relation is the universal relation. What is a universal relation? If all the elements of A are present in the relation, that relation is said to be called as universal relation, and that relation is equal to A cross A in the case. This will be relation. Now we are going to learn some more types of relations. Third one is the reflexive relation. A relation is said to be reflexive if it is related to the same element. For example, if A comma A belongs to the relation which connects A cross A, for every A, then R is reflexive. Let me give you an example to make it clear. Example, we have a set, say A is equal to 1, 2, 3. This is a simple set. And what will be A cross A? That we need to find out now. A cross A is equal to the set 1, 1, 1, 2, 1, 3, 1. Okay, that's it. Then it comes 2, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and 3, 3. These many elements are present in this set that we have already learned, that is PQ. Here it is 3 terms, so 3 into 3, 9 terms will be there. 1, 2, 3, 4, 5, 6, 7, 8, 9 terms are there. If R is a subset of A cross A such that R is equal to 1, 1, 2, 2, 3, 3, then R is said to be reflexive based on taking A as a set. R is said to be reflexive. The fourth type of relation is called as the symmetric relation. Symmetric. The name suggests that there is some symmetry. Symmetry means almost meaning to be a similarity. So what could be the definition of that? If A comma B is an element, A comma B is an element of this relation of R, then B comma A should be an element of R. I am not writing the perfect definition, but the simple meaning of what this relation means. Symmetric relation means if A comma B is one of the elements of this relation, that means that B comma A is also an element of R such that it becomes a symmetric relation. Let me take the same example where A is equal to 1, 2, 3. A cross A, as I have already found out in the previous one. I'm not going to write that again. So now we'll take one R relation that connects A cross A. That's a subset of A cross A. So let me take one relation, say 1, 2, 2, 1, 2, 3, 3, 2. These elements are enough, I think. Yeah, and I have took 4 elements here. So these two are symmetric. As you can just see, 1, 2, 2, 1. One is the opposite of the other. If I take this as A now and this as B, this one could be the element A comma B. Then this becomes the element B comma E. That means if A comma B is present, B comma A also should be present in this relation. Then it becomes symmetric. So in the same way, if this is A comma B, that means that this is B comma A, or vice versa of that. So hence when A comma B is present, B comma A should also be present to make the relation symmetric. The fifth type is the transitive relation. This is a bit tricky to understand, so see properly. Okay, let it be the same example I'm going to do later. If A comma B belongs to the relation R and B comma C belongs to relation R, then A comma C should belong to R. So what do we mean by this? So we have an element A comma B and another element B comma C already we have, and we have seen that element. If this element A comma C is also present in R, then the relation becomes transitive. So the condition is A comma B and B comma C should be present. If B comma C is not present, there is no transitivity. It is simply transitive. I'll explain once more. I'll take the example and explain. The example is the same. A is equal to 1, 2, 3 and R is a subset of A cross A. Now I'll take R such that it becomes 1, 2, 2, 1. I'll name this as R1, 2, 1. Okay, sorry, 2, 3 and 1, 3. Let it be these 3 elements. So let us check whether this is transitive. I do not know whether it's transitive or not. So yeah, let us consider this as AB. 1 is equal to A and 2 is equal to B. This is one element and this element is let 3 is equal to C. If A comma B is present and B comma C is present, we can see that both these are present. that means that A comma C, that is 1 comma 3 should be present. That is what is present here. That is the first case. Now we will defer it and try once more. Now we'll take 2 as A and 3 as B. So we have A comma B present, but there is no B comma C present. So there is no question against transitivity of that. That means that this is transitive. Let me take one more relation. 3 comma 1, 3 comma 3. This is enough, I think. We'll check whether this is transitive now. Yeah, here you can see that, let us consider this as A, this 3 as A, and this as B. 3 is A and 1 is B. There is no B comma C term, so there is no question against transitivity that arises in this case. Now we'll take this 3 as A and this 3 as B. So we have now A, B. There is one more B, C I can find here. Because this is 3, this is also 3. Therefore this is B and this is C. So what we mean is, now A comma B is present, that is 3 comma 3, and B comma C is also present, that is 3 comma 1. So what should be present? A comma C should be present. What is A? A is 3 and C is 1. That means that 3 comma 1 should also be present. That is already present. So we can see here. That means that this relation is also transitive. But there is one more important type of relation that turns up from these three cases. That is reflexive, symmetric and transitive. If a relation in a set A, if a relation in say some set is reflexive, symmetric and transitive, all the three cases should arise, then the relation is called equivalence relation. Equivalence relation. Equivalence relation. This is also an important thing. Many questions come just to prove that a relation is equivalence relation. Let us take an example for an equivalence relation. I am feeling bored taking the numbers 1, 2, 3 and all. Now let it be a relation say A is a set of all triangles. Okay, if I write the word set, I need not put the bracket. Set of all triangles, or I can represent it as some T where T is a triangle. Now my relation is based on congruence. R is equal to T1 comma T2 if we need the condition here. What is the condition? T1, the triangle T1 is congruent to T2, where T1 and T2, this is 1 and this is comma, that belong to this Cartesian product of that A cross A. they belong to this. That means all the triangles come under that. Now we need to check whether this relation is equivalence. The first case, you need to find whether it is reflexive. First one is reflexive. If it is reflexive, that means that T1 is congruent to T2. Let me write the symbol. T1 is congruent to T2, where T1 is equal to T2. That implies that T1 is congruent to T1. Or I need not write all these things. I can just conclude that it is T1 is congruent to T1 because it's the same triangle. The second one is the symmetric. If T1 is congruent to T2, this is a condition. That means that T1, T2 is one of the elements of R. If T1, T2 is one of the elements of R, T2, T1 should be an element of R to make it symmetric. So from the just simple methodology, we know that T1, T2 is also congruent to T1. You can write it T2 congruent to T1 or T1 congruent to T2. It means the same. So T2 is congruent to T1. That implies that T2 comma T1 is also an element of R. Similarly, we need to write it here also. T1 comma T1 is an element of R. Now we'll take the third case, that is a transitive. What does the transitivity say? For transitivity, we know that we need two conditions. That means two elements should be there. That is, if T1 is congruent to T2 and T2 is congruent to T3. Just we'll draw a triangle. Maybe one is congruent to the other. If this triangle is congruent to the second triangle and second triangle is congruent to the third triangle, that means that the first triangle is congruent to the third one. That is obvious. From that we can conclude that then T1 is congruent to T3. Therefore, the given relation is equivalence relation. So, to prove that a given relation is equivalence relation, you need to find these three cases. As a general case, you can prove if it is true. If it is not true, we can just show a counter example to just prove that it is not reflexive. One more example from the exercise to check. Okay, this question is to check if it is a equivalence relation and not to prove that. That means you do not know whether it's an equivalence relation or not. You do not know whether it's reflexive or symmetric or transitive. We need just to check and then prove all that. So the first one is reflexive. But one thing, when you find that check if it is the equivalence relation, most of the times you can see that it is not an equivalence relation. And to just prove by some small things. Okay, yeah. If it is only reflexive, if L1 comma L1 is an element, L1 comma L1 should belong to R. So what is this? What is the relation? L1 is perpendicular to L2. Say a line here, L1. Can the line be perpendicular to itself? It's nonsense. That means that L1 comma L1 cannot be an element of this relation. But this is not possible. Therefore, R is not reflexive. The second one is symmetric. We need to find whether it is symmetric. Say L1, if L1 comma L2 belongs to R, then what happens? So we'll just check and then write one simple statement. L1 is this one and L2 is perpendicular. This belongs to R, that means that it is already a perpendicular one. This is perpendicular and this is L2, 90 degree. If L1 is perpendicular to L2, that means that L2 is also perpendicular to L1. That means the same. Then L2 comma L1 also belongs to R. Therefore, R is symmetric. The third part is the transitive. How to prove it is transitive? That means that now we need two, that is A, B, B, C. Here we need L1, L2 belong to R and L2 comma L3 belongs to R. So we'll just check how it can be. Now we have already two lines here. L1 is perpendicular to L2 and L2 is perpendicular to another line. That means that a line is like this itself. If it is perpendicular to L2, L2 is a straight line or you call a vertical line and L1 is a horizontal line. So we need a horizontal line itself to get a perpendicular for the vertical line. Therefore L3 is horizontal itself. So now if L1 comma L2 belongs to R and L2 comma L3 belongs to R, that means that if it is transitive, L1 comma L3 belongs to R. Or what is the relation? L1 is perpendicular to L2. That means that L1 should be perpendicular to L3. Is it possible? Here L1 is horizontal line and L3 is also horizontal line. Therefore this is not possible. But L1 comma L3 does not belong to R. Therefore R is not transitive. What is the conclusion? What is the question and what is the conclusion now? From these three we can find out that it is not reflexive, it is symmetric, but it is not transitive. For R should be an equivalence relation, it should be reflexive, symmetric as well as transitive, but it is not there here. Therefore R is not an equivalence relation. Got it? Now we'll go to the next part. For learning a new concept, I opted the question 5 of exercise 1.1. This question is, show that R is a relation here in set A. A is 1, 2, 3, 4, 5 given by R is equal to A comma B if A modulus of A minus B is even. There is a similar question in example 5 in page number 3 of the textbook. Based on that, I can do this. So when I need to prove that it is an equivalence relation, I always take a general terms. Now this is the answer. So if it is a reflexive first one it should be. If it is a equivalence relation, it should be first reflexive. How to check whether it's reflexive? A minus B is even. Now here in this question we are just considering 0 is also an even number. But generally we talk that 0 is neither even nor odd and such things. But in this question we are considering 0 is even. So for it to be reflexive, the element a comma a is even, or let me write it, is belongs to R because modulus of a minus a is even, or 0 is even. Therefore R is reflexive. The second case, symmetric. If it is symmetric, that means that one element is already present. If element a comma b belongs to R, then modulus of a minus b is even. That is what we have already. If modulus of a minus b is even, then modulus of b minus a is also even. Because it's inside the modulus sign, we can take only the absolute value of that. So the negative sign is vanishing, and both of them give the same value. Therefore, b minus a is also even. That complies that b comma a also belongs to R. The third one, okay, let me write, therefore symmetric. The third one is, it should be transitive. If it should be transitive, there should be two elements, say a comma b and b comma c, that belongs to R. That is, modulus of a minus b and modulus of b minus c is even. In the cases we are going to add, and by the law of adding we also know that even plus even is also even. So by adding a minus b and b minus c, we get modulus of a minus c. If both these are even, even plus even, you get an even. That complies a minus c is even. Therefore, a comma c also belongs to R. That means R is symmetric. No, transitive. If R is transitive. From these three cases, as all of them satisfy, it is symmetric, transitive, as well as reflexive. Because all three are satisfying, R is an equivalence relation. So some special things you can find out here. If you take a number 1, what can the terms be? It can be either 3 or 5. 1, 3, 5. This is one set. Another set, we have 2. We take the number 2 now. If 2 can be one of the elements of this, that means what could be other element in this? It can be either 2 itself, as in this case, or it can be 4 only, because 4 minus 2 is only even. If 4 minus 3, you'll get an odd number, so it is not divisible by 2, so it should be even. So in this case, you can find out that 1, 3, 5 are related to themselves and not to 2, 4. This is a different set and this is a different set. You can just imagine that 1 is related to either 1, 3 or 5. 3 is related to 1, 3 or 5. 5 is related to 1, 3 or 5. That means only so many elements are present in this equivalence relation. If 2 is the first element, either it is related to 2 or it is related to 4. If 4 is the first element, it is related to 2 or to 4. So each one is called as the equivalence class. Equivalence class. Why it is called as a class? This is also a class, this is another class. Because they do not mingle with each other. They are separate and they are separate. Even though they are present on the same set, here they behave as different sets. That's it. Because it's called as a equivalence class. So this equivalence class can be represented as equivalence class of 1. This is a square bracket, not this flower bracket. This is a square bracket. Here it can be represented as a square bracket 2. This represents you need to find the equivalence class of 2. Now I'm going to start with the exercise 1.1 first question. The first question is to check whether the given relation is reflexive, symmetric or transitive. So the first subdivision is given set A is equal to 1 to 14, then R is a relation x comma y such that 3x minus y is equal to 0. If first case, it should be whether it should be reflexive. If it is reflexive, then x comma x should belong to R. We need to check whether x comma x belongs to R. For what value of x it belongs? 3x minus x is equal to 0. That means 2x is equal to 0 or x is equal to 0. But 0 does not belong to A. Therefore, this R is not reflexive. The second one, symmetric. If it is symmetric, x comma y belongs to R. If x comma y belongs to R, y comma x should also belong to R. Let me give you a counter example such that this is not possible. That's easier to explain in this case. Let me take the numbers 1 and 3. X comma y, 1 comma 3 belongs to R. I have just checked just now. Based on 3x minus y is equal to 0, I have taken x as 1 and y as 3. This becomes 3 minus 3, as that is equal to 0. That's what. Then if it is symmetric, that means that 3 comma 1 should also belong to this. I'll check whether it belongs to R. For that I need to substitute 3 in place of x and 1 in place of y. 3x minus y is equal to 0. I am applying x is equal to 3 and y is equal to 1. So what do you get from there? 3 into 3 is 9. 9 minus 1 is 8. That is 8 is equal to 0. What an absurd result. That means that 3 comma 1 does not belong to R. Therefore, R is not symmetric. Let me write this reflexive part to explain the transitive one. Transitive. How do I explain the transitive one? Let me take an example once again. I'll take numbers 1, 3 same. 1, 3 belongs to R. So now I'll apply x as 3. What I get as y? 3 into 3 minus y is equal to 0. Then y becomes 9. Therefore, 3 and 9 belongs to R. 3 comma 9 belongs to R. That I have found out just now using this equation. So I need to get 1 comma 9 is one of these. 3x minus y is equal to 0. X is equal to 1. Y is equal to 9. 1 and 9. Therefore I am substituting here 3 into 1, 3 minus 9 is equal to 0. 3 minus 9 is minus 6 is equal to 0, and how can be some nonsense result I am getting. Therefore Or simply, instead of doing this explanation, you can just write that 1 comma 9 does not belong to R. Therefore, R is not transitive. This explanation is just for you to understand. This you need not write. You need to just understand that 1 comma 9, why does it not belong to this relation? That's it. Now we'll go to the second question. The second question states that from the set of natural numbers, that is n, that is the set on which R is applied, the R says x comma y if y is equal to x plus y and x is less than 4. X is less than 4 and it belongs to the natural numbers. That means whatever values x can take. It is 1, 2, 3. Maybe I can write that set here instead of writing the natural numbers. Okay, y is not belonging over here. That's why I did not write. So first one is reflexive. Let me give a counter example and just explain this. I'll take 1, 1. 1, 1 doesn't belong to R because 1 is not equal to 1 plus 5. Why did I write this? This is based on this equation. This is y, this is x, y. So where y is there, I am applying 1. Where x is there, I am applying 1. 1 is equal to 1 plus 5. But that is not equal. So I am writing not equal to. Therefore, R is not reflexive. Now, let me take symmetric. Oh, I'll take some number now. But if I apply x as 1, y will be 1 plus 5. See, y is equal to x plus 5. So it is 1 plus 5, that is 6. This belongs to R. Then 6 comma 1 should belong to R if it is symmetric. So I'll instead of applying, I'll just write that. But 6 comma 1 doesn't belong to R. Therefore, R is not symmetric. Did you understand? I'll just explain. I'm taking one of these values because x is less than 4. So I'm taking a simpler one for me. So x is equal to 1. I'm putting 1 plus 5. I'll get x as 6. So x comma y. So y is 6 here. So if a comma b is belonging to R, for it to be symmetric, 6 comma 1 should also be belonging to R. But this is not belonging. Just by saying you can explain that. The third one is transitive. I'll take the same thing. 1 comma 6 belongs to R. Oh, I'm feeling a doubt that whether I have a case against transitivity here, because the smallest number that comes at the place of y is 6, and that cannot come in the place of x because x is less than 4. So there will be no term that starts with 6 and with one more term. Therefore, there is no question against transitivity. So can I just explain that R is transitive because a comma b exists but b comma c doesn't exist. For any a. Therefore, it is transitive only. This function is given as transitive only. We have the next question from exercise 1.1, first question. That is third and fourth I have written here now. This is to check whether it's equivalence relation. The first one is however reflexive. I'm going to do it a bit faster now. If it is reflexive, that means that x comma x belongs, or what does it state? If x comma x is belonging to R, therefore x is divisible by Yeah, that is true. Therefore, R is reflexive. The second one, symmetric. Let me take an example, because it looks like it is not going to be symmetric in this case. So let me take an example. 2 comma 4 belongs to R. If 2 comma 4 belongs to R, that is 4 is divisible by 2. It is true. 4 is divisible by 2. That means that 2 comma 4 is belonging to R. That I know. Just now I found out. But 2 is not divisible by 4. Therefore, R is not symmetric. R is not symmetric. Now we'll go to the third case. Let us transitivity. Transitive. How do you find out that? Yeah, just check a simple one. If A comma B and B comma C that belongs to R, that means that B is divisible by A and C is divisible by B. Therefore, from this you can just see. I'll take an example and explain how it is true. So let me take this number. A as 1, B as 2 and C as 4. So if 2 is divisible by 1, that is true. That is B is divisible by A. Let me take this as C and this is B now. Now 4 is divisible by 2. That also I know. Now what will be the A comma C term? That is 4 comma 1. That is 4 is divisible by 1. Based on this example, I am writing that C is divisible by A. From this, you can just explain that A comma C belongs to R. Therefore, R is transitive. R is transitive. Let me rub this now. This is the next one. Before this, I need to tell you the properties of integers. Subtraction under integers is closed, and hence an integer minus an integer will be always an integer. So what is the condition here? X minus y is an integer, and this is the group of integers. Z stands for set of integers, right? Yes. Now again the same thing, reflexive. A comma A belongs to R, that is A minus A is integer. What is A minus A? A minus A is 0. This is obvious. 0 is an integer. Is it a doubt? It is an integer. The second one, symmetric. How to find a symmetric? A comma B belongs to R. Therefore, A minus B is an integer. I'll take one minus sign outside such that B becomes positive. Okay, I'll just show you that. Minus I am taking outside, and this B becomes positive, A becomes negative. B minus A is an integer. This minus doesn't matter because it is just an integer. So this minus is also an integer. Minus 1 into. So integer comes under negative numbers also. Therefore, B minus A is also an integer. Therefore b comma a belongs to R, therefore symmetric. The third one, transitive. A comma b belongs to R and b comma c belongs to R. That is a minus b and b minus c are integers. Another property of commutative closure of integers is also that addition of two integers are also integers. So if I add these two, a minus b and b minus c, a minus b plus b minus c, this becomes, that is also an integer. If that is also an integer, a minus c is an integer. That is a comma c belongs to R, therefore R is transitive. That is what we infer from this. Now we have the question from exercise 1.1, second question. If the relation R that is from the real numbers that says a comma b, if a is less than or equal to b square, you have to show that it is neither reflexive nor symmetric nor transitive. So how do you need to show this? The first one is reflexive. Let me just give an example. I'll say half comma half doesn't belong to R, therefore R is not reflexive. Yeah, I think this much is enough. I'll just explain how it's get. A comma A. Okay, let me apply this condition and see. If this is A and this is B, A should be less than or equal to B square. Half is less than or equal to 1 by 2 whole square. That is 1 by 2 less than or equal to 1 by 4. But this is wrong. Therefore, it does not belong to the relation R. That's what. This much is what you need to understand. And I think this much is enough if you write. The second one is symmetric. We need to just give an example. Say 2 comma 6 belongs to R, but 6 comma 2 doesn't belong to R. This is one of the cases. You need to just give one example is enough to show that it is not symmetric. Therefore, R is not symmetric. So I'll just explain how we got this. A, B, this is A, this is B. A is less than or equal to B square, 2 is less than or equal to 6 square, then B, you know that 2 is less than or equal to 36. This is correct. I know that this belongs to this relation. How I should check whether this does not belong to that relation? 6 is less than or equal to 2 square. 2 square is 4. 6 is less than or equal to 4. But this is not true according to this relation. So this relation is, this element does not belong to that relation. That's what we find. Next we'll go to the transitivity. Transitive. Again, even in this case too, we are going to take a counter example. So let me take one example, say 2 comma minus 5 that belongs to R. I'll check whether this is belonging. A should be less than or equal to B square. A is 2. 2 should be less than or equal to B. B is minus 5. Minus 5 whole square is 25. That complies 2 is less than or equal to 25. Yes, we know that 2 is less than 25. So this is correct. And minus 5 comma 0. This is A, this is B. Again, we'll just check the relation. Minus 5 less than or equal to B is 0. 0 square is 0. Minus 5 is less than 0. This is also correct. This also belongs to R then. But 2 comma 0. Does it belong to R? We'll check now. 2. This is A. 2 is A. Less than or equal to B is 0. 0 square. 2 is less than 0. This is a wrong statement. Therefore, this does not belong to R. That implies that R is not transitive. Yeah, now we have the third question, which says we need to check whether this relation is reflexive, symmetric, or transitive. The first one is reflexive. Seeing the question itself, we do not know whether it is really reflexive or not. I need to just check it. So if it is reflexive, that means 1, 1 should belong to that set. That is set or the relation, what you call. It is R. So let me check whether 1 belongs to R. 1 plus 1 is equal to 1. This is A and this is B. This is a meaningless relation. That means I think this is not wrong. Yes, that means that R is not reflexive. Second one is symmetric. For proving symmetric, let me take one more example. Just I'll check whether it is going to be symmetric. 2 comma 3 belongs to R. 2 comma 3 belongs to R. But as this is a plus 1, I feel that it's not going to be symmetric here. So, but 3 comma 2 does not belong to R. Let me check that once again. In this case, A plus 1 is equal to B. 2 plus 1 is equal to 3. Correct. In this case, A is 3. So 3 plus 1 is equal to 2. This is wrong. So by seeing this example, you can see that it is not symmetric. R is not symmetric. Next example. Okay, next part is the transitivity. For proving transitivity, we need to take a different one. Example. 2 comma 3 belongs to R and 3 comma 4 also belongs to R. Let me check whether it's really because it's just x plus 1 is equal to y. X plus 1 is equal to y. That means that the second term is 1 more than the first term. That's what I can see here. But 2 comma 4 does not belong to R because the second term is 2 more than the first term. Hence, you can show that R is not transitive. Yes. Now we found out that it is neither reflexive, nor symmetric, nor transitive. Now we are going to have the fourth question of the exercise 1.1. The question says relation R is equal to AB, where A is less than or equal to B in the set of real numbers. We need to show that the relation is reflexive and transitive but not symmetric. Now we know what we have to prove. So it's easier than the previous one. So to show that it's reflexive, you need to just show that every A comma A belongs to the relation R. I am here showing the relation R. This big R is a set of real numbers, so that I can just differentiate between those two. So every A belongs to R. How I should just prove that? So A is less than or equal to A, or A is equal to A. That is true. Always. Therefore, R is reflexive. Now we are going to symmetric. for symmetric, it is given that it is not symmetric. So easy, you can give a counter example here. So let 0, 2 belong to R because 0 is less than or equal to 2. A is 0, B is 2 here in this case. So 0 is less than or equal to 2. This we know. But 2, 0 does not belong to R. How can 2 be less than or equal to 0? That is not possible. So considering this counter example, R is not symmetric. Yes, R is not symmetric. Next, going to the transitive. It is in the question it is given that it is transitive. We have to prove that it is transitive. So you need to take a general statement. So if A, B belongs to R and B, C belongs to R. What is the meaning that it is belonging to R? It means that A is less than or equal to B. A is less than or equal to B. From this you can find out that B is less than or equal to C. From these two statements I can combine and write A is less than or equal to C. Therefore A, C also belongs to R. Therefore R is transitive. Transitive. This is what is given in the question. You can just save, understand. I'm going to skip the question 5th one because it's very similar to the 3rd one. Because it's just a cube and square difference, that's it. In the 6th question we have the relation R is equal to 1, 2, 2, 1 in the set 1, 2, 3. What is given in the question? It is given that we need to prove that it is symmetric but neither reflexive nor transitive. It is symmetric, neither reflexive nor transitive. That means that here we are going to take a general statement and in these two cases just give a counter example against this. Okay? Yes. If it needs to be reflexive, then 1, 1, 2, 2 and 3, 3 should belong to R. But that does not belong to this relation. Therefore, it is not transitive, not reflexive. For taking a symmetric, here we have 1, 2. Yes? Its opposite one is 2, 1. That means it is reflexive. That is 1, 2 exists, or in other words you can say it is belonging to that relation. That implies that 2, 1 is also belonging to that relation. These two you can see, or the vice versa. And no opposing elements present. Opposing, in other words, I can just say that there is one, if there is some more elements such that they oppose the symmetry of that relation, then they cannot be called as symmetric. But here there is nothing like that. See, in the transitive, it is given it is not transitive. So just give a common example. So here 1, 2 and 2, 1 belong to R. That means that if it is transitive, A, C, that is 1, 1 should belong to R. But 1, 1 doesn't belong to R. Therefore, it is not transitive. That's it, what you get here. 7th question is a simple one. 8th question I have explained as example 5 to explain about the equivalence class. Now you are going to the 9th question, and in this I am just going to explain how to find the elements related to 1 in each case. Because this is a question that is similar to the example 5 that I have explained for understanding what is equivalence class, and that is a very simple relation from this. So after proving that it is equivalence relation, R is equivalence relation in both the cases. Yeah, in both the cases, still here you need to just prove that it is reflexive, symmetric and transitive based on the general statements. Next, how do you need to prove, how do you need to find the elements that are related to 1, that is the equivalence class of 1. equivalence class of 1 is the set of all the numbers that are related to 1 in the given relation. So all the numbers that can be related to 1 in that relation could be how many? Just we need to see. So this is based on the set A. R is given based on the set A, and here x belongs to 0 to 12 and it is the integers only, not all the real numbers come under that. Yes? Now how do we do this? A minus B is a multiple of 4. That means that the difference between A and B should be a multiple of 4. So 1 minus 1, considering 0 also to be a multiple of 4, or the 0th multiple of 4 to be 0, we are considering 1 is related to 1. That's how you show that it is a reflexive relation over there. So in the second case, you need to get 5 here. It is related to 5. How is it related to 5? 5 minus 1. 1 comma 5 belongs to R. That means that 1 is related to 5. Yes? So 5 also comes under the equivalence class of 1. So plus 4. Because it's the multiple of 4, I need to add 4 to 5. That comes 9. 9 plus 4 is 13. But 13 does not belong to this set A, because it's only up to 12. So this is the equivalence class of 1. Yes? So we'll see how this equivalence class is. See, here the equivalence class is 1 if A is equal to B. That means it's only reflexive in this case. Symmetric doesn't arise at all because there is no extra like A, B term. It's A everywhere. So there is no extra thing that comes to be transitive. So the only element that comes in the equivalence class of 1 is 1 itself, because it's a reflexive relation, completely reflexive. Now we have the 10th question of exercise 1.1. The question says just to give the examples of different things. So now we have symmetric but neither reflexive nor transitive. Let us have a relation for a set A. A let us call as 1, 2, 3. It should be symmetric but not reflexive nor transitive. So let the relation be something like 1, 2, 2, 1. This is, you can just see that this is AB, BA. So it is symmetric here. It does not contain 1, 1, 2, 2, 3, 3 such terms. So it is not reflexive. If 1, 2 and 2, 1 are present, 1, 1 should be present. But that is not present. Hence it is not transitive also. So now we need to have transitive but neither reflexive nor symmetric. So we'll take a relation, say R is equal to A comma B. A is less than B. So transitive is possible because it is just like integers or are in real numbers. Yes? So the same number cannot be less than or less than that same number. Like 1 is not less than or equal to 1. Hence it is not reflexive. It is not symmetric because if 1 comma 2 belongs to this, that is 1 is less than 2. Yeah? 1 is less than 2. 2 cannot be less than 1. So that 2, 1 belongs to that. So this is wrong. Only this is possible for this. Hence it is not symmetric, but it is transitive. Yes? Now we'll go to the third one, that is reflexive, symmetric, but not transitive. The simplest one to give for that is, see, I'll take the same, this one, that is 1, 2, 3. Yes? R is equal to 1, 1, 2, 2, 3, 3, 1, 2, 2, 1, 1, 3 and 3, 1. Yes, this much is enough, I think. By these three elements you can just show that it is reflexive because 1, 1, 2, 2, 3, 3 is present. 1, 1, 2, 2, 3, 3. Yes, it is symmetric because 1, 2 is present means 2, 1 is also present here. 1, 3 is present, that means 3, 1 is also present here. but it is not transitive. How can show this? We can see that one. Okay, we'll see this one. 1 3 is present. Yeah. Okay, let us take something else. Maybe, yeah, we'll take 2 1. 2 1. 2 1 belongs to this relation, and 1 3 belongs to this relation. Yes. A comma B, B comma C belongs to this relation. Then 2 comma 3 should belong to that relation. But where is that element? The element is not present in this relation. That means you can just say that it is reflexive and symmetric, but not transitive. What could be the fourth one? The fourth one is you need to show that you need to get a reflexive, transitive, but not symmetric. Yes. For that, it's a simple one. Take an example. A comma B, then A is less than or equal to B. If A is less than or equal to B, that equal to sign indicates that it can be reflexive, right? If A is less than or equal to B. So in this case, we found out that when it is less than B, it is transitive. Let's simpler to conclude than take an example and explaining. Since it is equal, it is reflexive. Since in this case we found out how it was transitive, based on that I can conclude that this relation is also transitive, because it has just one more case, that is A is equal to B also. That's it. Therefore it is not symmetric in this case. What will be the last one? Yeah, now we have the fifth one. We need to show some relation that is symmetric, transitive, but not reflexive. We need to take care that the reflexive term do not enter over there. For that, let me take a set. Say 1, 2. This is enough, I think, 2 terms. Now we need to have a relation such that both 1, 1, 2, 2 are not present. Either one is okay, I think. So let me take 1, 1, 1, 2, 2, 1. Right? By saying this, we can make out that it is symmetric. 1, 2, 2, 1 is present. There is no other element that shows symmetry over there. Then to show transitivity, 1, 2 is present. Yes. 2, 1 is present. So 1, 1 is also present. Right? A, C. 1, 1 is also present here. Right? Next, which is, yeah, 2, 1. 2, 1 is present. Yeah, 2, 1 is present. But, and 1, 1 is also present. So, 2, 1, A, C. 2, 1 is also present, right? That's it. Yeah, now we have the fifth question, that is we need to get an example of a relation that is symmetric, transitive, but not reflexive. So just we'll give a condition such that it cannot be reflexive. Say R is a relation that is A comma B such that A is not equal to B. If A is not equal to B, it can never be a reflexive relation. So surely it is a symmetric and a transitive relation. The simpler way to just give that it is not reflexive. Okay. Now we have the 11th question of exercise 1.1. The first part is to just prove that R is an equal relation. That we know already, so I'm just going to skipping that step. The second part of the question says we need to show that the set of all the points that are related to the point P. Say you have a point P, then the set of all the points that are related to that point P is a circle passing through the point P in which origin is the center. So what is the meaning of this? So you have the origin here and say P is some point here. All other points that are related to this P form a circle. Yes, with O as the center. Right? So that's what you need to prove here. Say this is P and there is something Q, R. So what is the meaning of this? So distance from this center, consider let it K. Yes, let the distance from origin BOP is equal to K units. Units is in length here, so now we need to prove that it's a circle. So all the points are at a distance K from the center, that is the origin. Based on the definition of a circle. What is the definition of a circle? I'll just tell now. What is the definition of a circle is the set of all the points on a plane that is equidistant from a given point. Here the given point is the origin. That's why it becomes the center. And all the set of all the points that are equidistant. Say the distance is k here. So all the points that are present on that plane with the distance k form the circle. Based on the definition of the circle, we can conclude that set of all points related to P form a circle with center O. I hope you get it. Here the center is O and all the points are equidistant from the center. Right? That's what you need to understand. That's how they form the circle. We will go to the next question. Now we have the 12th question. The 12th question has a set of all the triangles where R is a relation, that is T1 T2, such that T1 is similar to T2. It is a symbol which you use for showing that something is similar. I think we have learned in class 10. The first part is just to prove that R is an equivalence relation. That's again and again it's coming the same type of questions. The second part of the question is you have to just find out which triangles among the triangles T1, T2 and T3 are related. Here we have the sides of T1, T2 and T3 that is given in the question. 3, 4, 5 is the sides of T1, T2 is 5, 12, 13, T3 is 6, 8, 12. In class 10 you have learned for the similarity of two triangles the sides to be proportional. So in these three triangles we can find that the triangles T1 and T3 have proportional sides. How? Let us see. 3 by 6. 3 by 6 is equal to 1 by 2. 4 divided by 8. That is again 1 by 2. 5 divided by 10. That is again 1 by 2. That means that the ratio of the sides of triangle 1 and triangle 3 are equal. Or in other words, the sides are proportional. Therefore, T1 is related to T2. This is also another type of notation that we use to just show that T1 is related to T3. Right? Next, we have the 13th question now. Next question is question 13. This question has the set of all polygons A, that is having set of all polygons. Polygons could be number of sides. How many were? From 3 to 4, 5, 6 and so many. The first part is a relation where P1, PQ, this is x, y, and both have the same number of sides. They are related only if they have same number of sides. And you need to just prove the equivalence relation as done in the previous questions. So the second part of the question is you need to find the set of all elements that are related to a triangle T with the sides 3, 4 and 5. So the set of all the elements that have the triangle that have related to the triangle T with sides 3, 4, 5. This sides 3, 4, 5 is have no meaning here. There is no use of that given because all the set of all triangles are related to each other. Because it's just here it is just that it has same number of sides. So let me name the set of all the elements that are related to the triangle T as the equivalence class T, that is equal to the set of all T such that T is a triangle. T is a triangle. Yes, this is the answer for the 13th question. Yeah, now we have the 14th question. Here we have the set L. Here L is the set of all lines in the xy plane. Xy plane is the one plane that we generally take, and R is the relation that says L1 is related to L2 if L1 is parallel to L2. First we need to just prove that R is an equivalence relation as the same as again. And the second part of the question, what does it say? It says need to find the set of all elements that are related to y is equal to 2x plus 4. Generally the statement just says you need to find the equivalence class of y is equal to 2x plus 4 is the line. Yeah, if it should be related to some other line, say this is L1, if it is related to L2, then it should be parallel. If it is parallel, the slope is same. As we have learned in class 11, the slope of this will be 2. M is equal to 2. Why? This is in the format of y is equal to mx plus c. So this has to be corresponding to m. So everywhere m is equal to 2. Therefore the equivalence class of this becomes x comma y instead of writing the set in this format, I'll just write it as how it is here, and we'll write let it be y is equal to 2x plus c. Because the slope is going to be the same, maybe the intercept is changing for every parallel line, that is every line that is parallel to this given line. So c is belonging to the set of real numbers. That's it. This is the set of all elements that are related to the line y is equal to 2x plus 4. Only the intercept is going to change. That's it. Now we have the 15th question. The 15th question is just about the MCQ. How to solve the MCQ. Generally, that's very important for the competitive exams. So the first question, the 15th question is, it has the set 1, 2, 3, 4. Yes. Then what is the given relation? R is equal to set 1, 2, 2, 2, 1, 1, 4, 4. Then you have 1, 3, 3, 3, 3, 3, and 3, 2. These are the elements that are there in there. R, I'll check once more. It has 1, 2, 2, 2, 1, 1, 4, 4, 1, 3, 3, 3, and 3, 2. Yes, you need to check whether it is reflexive, symmetric, and transitive. This is just fast. Let's just do it. This is the relay 15 question. This is the set. So it should have 1, 1, 2, 2, 3, 3, 4, 4. 1, 1 is there, 2, 2 is there, 3, 3 is there, 4, 4 is there. So reflexive, correct. Reflexive, it is reflexive. If it is, it should be symmetric now. 1, 2. If 1, 2 exists, 2, 1 should exist. Where is 2, 1? 2, 1 is not present. So it is not symmetric. Symmetric? No. Transitive. If it should be transitive, that means if say 1, 3 is present. Yeah, 1, 3 is present. Then 3, 2 is also present. That means 1, 2 should be present. That is present. There is no problem now. So this is alright. It is transitive, I think. Yes. So seeing this, what I can understand is the given relation is reflexive and transitive. Where is the option? The option B says R is reflexive, is transitive, but not symmetric. So the answer is going to be option B. So we'll go to the 16th question now. What is the 16th question? 16th question is also an MCQ now. We are just going to see what happens in this question. R is a relation in the set N where R is equal to A, B, such that A is equal to B minus 2. A is equal to B minus 2, where B is less than 6, where B is not less than, it's greater than, B is greater than 6. So you see the question. So what do you need to find in this? You need to find the correct answer where the relation belongs to. Yes? Say there are given elements. There is 2, 4 in the first option. Second option has 3, 8. Third option has 6, 8. And the fourth option has 8, 7. You should just check whether these elements belong to this particular relation. So here B should be greater than 6. So with this choice you can avoid, because B is 4, but here B is given to be greater than 6. This is not possible, right? Here, yeah, it is considering all the real numbers. So in every case, the first number should be 2 less than the second number. Here it is greater, so you cannot consider this case. If here, this should be 8 minus 2, because B is 8, A should be 8 minus 2, that is 6. So this is also not considered. The correct option is this one, because when you consider B is equal to 8, this is what I have written here. When B is equal to 8, A becomes 6. So A, B. So the option is going to be C. Thank you for today.